Hello, everyone. Tonight, we delve into the shadowed, dangerous, and decidedly unglamorous world of theoretical physics turned apocalyptic engineering. We're going to explore the story of how humanity built its first nuclear bomb. Forget the spy movies and the scowling generals moving pieces on a map. While all of that was part of the picture, the real story is far stranger, far more cerebral, and in a way, far more terrifying. It's a story of chalk-dusted blackboards, of sleepless nights debating the cross-section of a neutron, of the smell of ozone in a laboratory, and the quiet terror of realizing that your equations on paper could, quite literally, set the world ablaze. The truth is, you probably wouldn't last a single day in that environment. Tonight, you're not a bomber pilot or a politician making a fateful decision. You are a theoretical physicist with a migraine, a blackboard full of equations that won't quite balance, and the feeling that the fate of the world might depend on your ability to split an atom. So, before you get comfortable, take a moment to like the video and subscribe, but only if you truly enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who joins us from all corners of the globe. Now, dim the lights, perhaps turn on a fan for that soft background hum. And let's journey together into tonight's story. Imagine this. It's the frigid winter of 1938. The air in your Berlin laboratory at the Kaiser Wilhelm Institute smells of ozone, hot metal, and the dust of decades of discovery. You are a chemist, perhaps one of the world's finest, like Otto Hahn, and for weeks, for months, you've been bombarding uranium with strange, slow particles called neutrons. The idea, inherited from the great Enrico Fermi in Rome, is to create elements heavier than uranium, transuranic elements that no one has ever seen. It's an alchemist's dream come true with 20th century science. But something isn't working. Something is profoundly strange. Alongside your colleague, Fritz Strassmann, you perform the experiments again and again with almost painful precision. And the results are absurd. Instead of finding heavy elements near uranium on the periodic table, you keep finding barium. Barium, an element almost halfway down the table. It's as if you shot an elephant and it turned into two rabbits. It's impossible. It's madness. Perplexed, you write to your former collaborator, Lise Meitner, a brilliant physicist who has had to flee Nazi Germany due to her Jewish heritage and is now exiled in Sweden. Now, transport yourself to a small Swedish village near Gothenburg. It's Christmas. Snow crunches under your boots. You are Lise Meitner, and you've just received Hahn's perplexing letter. Your nephew, Otto Frisch, also a refugee physicist, is visiting. You go for a walk in the snowy forest, he on his skis, you walking briskly to stay warm. As you walk, Hahn letter gnaws at your mind. Barium. How is it possible? Suddenly you stop. An idea strikes you. An image that Niels Bohr, your mentor, had suggested years before. The nucleus of an atom behaves like a liquid drop. If a neutron strikes a uranium nucleus, which is already large and unstable, the drop doesn't just deform. It wobbles, elongates, forms a waist in the middle, and then it splits in two. It fissions, like a living cell dividing. Frisch and you sit on a fallen log in the middle of the silent winter forest and begin to make calculations on scraps of paper. You use Einstein's most famous equation, E equals mc squared, which until that moment was more a theoretical curiosity than a practical tool. You calculate the mass of a uranium nucleus and the mass of the two resulting pieces, like barium. There's a difference. A tiny, minuscule amount of mass is missing. And according to Einstein, that mass hasn't vanished. It has been converted into an absolutely colossal amount of energy. Your preliminary calculations show that the fission of a single uranium nucleus releases enough energy to visibly jump a grain of sand. It seems small, but you realize that in a piece of uranium, there are more atoms than grains of sand on all the beaches in the world. The potential is dizzying and terrifying. Frisch returns to Copenhagen and tells Niels Bohr what you've discovered, just as Bohr is about to embark for America. Bohr slaps his forehead and exclaims, "Oh, what idiots we've all been! It's wonderful, but it must be so." The news crosses the Atlantic with Bohr. Meanwhile, in New York, another Hungarian refugee, the brilliant and perpetually worried Leo Szilard, heard the news and felt a chill. Unlike many of his colleagues, who saw only the beauty of physics, Szilard saw the geopolitical chessboard. He had already conceived the idea of a chain reaction in 1933, while waiting to cross a street in London. The idea that if a nuclear reaction released neutrons, and those neutrons could initiate other reactions, an explosive cascade of energy could be created. Now, with uranium fission, the mechanism was real. And Szilard knew something else. Uranium fission didn't just release energy and two smaller nuclei. It also released 2 or 3 additional neutrons. Those neutrons were the key. They were the sparks that could set the entire forest ablaze. Szilard, a man who had fled Nazi tyranny, was terrified by the idea that German scientists, the same ones who had discovered fission, might realize this and build a weapon for Hitler. He began a frantic campaign to urge the scientific community to keep silent, a futile attempt in a world where knowledge is free. Desperate, he sought out the only person in the world with the moral authority and public recognition to warn the American government, Albert Einstein. In the summer of 1939, Szilard and his colleague Eugene Wigner drove to Long Island to find a relaxed and oblivious Einstein enjoying his vacation. They explained the chain reaction. Einstein, the pacifist, was stunned. "Daran habe ich gar nicht gedacht," he said. "I hadn't even thought of that." Szilard drafted a letter. Einstein signed it. And through an intermediary, the letter reached President Franklin Delano Roosevelt's desk. The letter warned of bombs of a new type and extremely powerful, and urged action. The world of theoretical physics, a world of snowy walks and equations on scraps of paper, had just knocked on the door of power. And power, albeit slowly, was about to answer. The spark had been lit. The long, dark road to the bomb had begun. Einstein's letter reached Roosevelt in October 1939, just as the world was plunging into the darkness of World War II. The initial response from the American government was lukewarm, to put it mildly. A uranium committee was formed, chaired by Lyman Briggs, a government scientist known more for his caution than his vision. The committee met, listened to the Hungarian physicists with their thick accents and their almost feverish urgency, and allocated the modest sum of $6,000 to purchase graphite and uranium for further experiments. To Szilard and his colleagues, it was an insultingly small amount, a sign that the bureaucrats didn't grasp the scale of what was at stake. Research progressed at a snail's pace, scattered across university laboratories nationwide, such as at Columbia University, where Fermi and Szilard were attempting to build a prototype reactor. But the true urgency, the real theoretical impetus that would transform possibility into terrifying certainty, came from an unexpected place, Great Britain. While the United States hesitated, across the Atlantic, 2 refugee physicists at the University of Birmingham, Otto Frisch, Lise Meitner's nephew himself, and Rudolf Peierls, were grappling with the same problem. In March 1940, in a country already at war and under constant threat of German bombing. They sat down to write what would become known as the Frisch-Peierls Memorandum. This document, barely 3 pages long, is arguably one of the most important and prophetic texts of the 20th century. In it, they did 2 revolutionary things. First, they addressed the question of critical mass. Until then, many scientists, including the great Niels Bohr, thought it would take tons of uranium to sustain an explosive chain reaction, making a bomb logistically impossible. Frisch and Peierls decided to calculate the critical mass not of natural uranium, but of its pure fissile isotope, uranium-235. Natural uranium consists of 99.3% heavy, inert uranium-238, and only 0.7% of the lighter, crucial uranium-235. Separating them was a Herculean task, but what if it could be done? Their calculations, though approximate, were astonishing. The critical mass of pure U-235 was not tons. It was perhaps a few kilograms, a sphere the size of a golf ball. Suddenly, the atomic bomb moved from the realm of science fiction to being a feasible engineering project. The second part of the memorandum was even more chilling. They didn't stop at physics. They described with chilling clarity the effects of such a weapon. They wrote about the explosion, equivalent to several thousand tons of dynamite. They described the fireball, the shockwave, and most importantly, they described the radioactive fallout. They warned that the radiation emitted by this cloud will cause death to all living beings over a wide area, and that the weapon could not be used without killing a large number of civilians. At a time when the world only thought of conventional explosives, they predicted the unique and terrible consequences of a nuclear weapon. Far from being just another weapon, it was a completely new category of destruction. This memorandum was the catalyst. It was delivered to the British government, which, unlike the American, reacted swiftly. They formed a top-secret committee whose deliberately dull codename was the Maud Committee. This committee brought together Britain's best minds and confirmed Frisch and Peierls' findings. Its final report in the summer of 1941 concluded unequivocally that a bomb was possible and could be ready in about 2 years. This British report was the wake-up call the United States needed. A copy reached Vannevar Bush, a brilliant MIT engineer whom Roosevelt had placed in charge of the Office of Scientific Research and Development, OSRD, an organization created to mobilize American science for the war. Bush was the perfect man for the job, a formidable organizer, a pragmatic visionary who understood both scientists and the military. When he read the Maud report, he understood that the game had changed. The British calculations were sound. The threat was real. And the United States, with its vast industrial resources and safe distance from the battlefields, was the only place where a project of this magnitude could be carried out. Bush went directly to Roosevelt. On October 9, 1941, 2 months before Pearl Harbor, he met with the president and presented the findings. It was no longer about $6,000 and a bit of graphite. It was about a total commitment, a massive industrial program to build a weapon that could decide the outcome of the war. Roosevelt listened carefully and gave his approval. The project would receive absolute funding and priority. The Uranium Committee was reorganized, given new impetus, and finally a code name that would become synonymous with secrecy and power: the Manhattan Project. The theoretical phase had ended. The phase of impossible engineering was about to begin. The foundations of chalk and paper had been laid, and upon them, secret cities and machines of a scale never before seen would rise. With the president's blessing and the impetus of the Maud Report, the American effort to build an atomic bomb transitioned from a scattered collection of academic research into a full-fledged industrial and military project. Vannevar Bush and his OSRD became the organizational brain, but they needed someone to execute the plan on the ground. The project's scale required a different type of leadership, one that could mobilize resources, intimidate contractors, and maintain absolute secrecy. In September 1942, they found their man, Brigadier General Leslie R. Groves. Groves was an engineer from the Army Corps of Engineers, famous for having overseen the construction of the Pentagon, a massive project he'd completed ahead of schedule and under budget. He was a burly, brusque, demanding man with almost limitless self-confidence. He knew nothing about nuclear physics, but he knew how to build big things fast. His initial reaction to being assigned the project was disappointment. He'd hoped for a frontline command, but he soon grasped the magnitude of his new task and tackled it with relentless energy. Groves, the pragmatic builder, needed a scientific director, a brain that could unify the world's most brilliant and often most egocentric theoretical and experimental physicists. His choice, to the surprise of many, fell to J. Robert Oppenheimer, a theoretical physicist from the University of California, Berkeley. Oppenheimer was, in many ways, Groves' polar opposite. He was thin, a chain smoker, fond of Sanskrit poetry, and had a circle of friends with known communist sympathies that horrified security services. He had no administrative experience and had never run a laboratory. Yet, he possessed extraordinary charisma, an incredibly quick mind that could grasp almost any area of physics, and palpable ambition. Groves saw in him something others didn't, a unique ability to inspire other scientists, and a deep understanding of all aspects of the project, from theoretical physics to engineering. He's a genius, Groves later said. A real genius. He knows about everything. He can talk to you about anything you want. Well, not everything. He doesn't know anything about sports. The unlikely partnership between the burly pragmatic general and the ethereal, brilliant physicist became the central axis of the Manhattan Project. With leadership established, the project was organized around several distinct fronts, each tackling a monumental scientific challenge. They realized there were two parallel paths to obtaining the fissile material needed for a bomb, uranium-235, and a new element, plutonium. Arthur Compton, a Nobel laureate from the University of Chicago, was put in charge of the metallurgical laboratory, whose primary goal was to research plutonium. In Berkeley, the inventor of the cyclotron, Ernest Lawrence, another Nobel laureate, would focus on one of the uranium separation methods. At Columbia University, Harold Urey, also a Nobel Prize winner, would investigate another uranium separation method. It was a titanic and decentralized effort, with research centers spread across the country, from Chicago to California and New York. Groves and the scientists faced a crucial decision: which method to pursue, uranium or plutonium? And if uranium, how to separate it? The uranium problem was fundamentally a separation problem. As we mentioned, uranium-235, the fissile isotope, constitutes less than 1% of natural uranium. The rest is U-238, which is chemically identical. They cannot be separated by chemical reactions. The only difference between them is a minuscule difference in weight, approximately 1%. Separating them is like trying to pick 3 specific marbles out of a barrel of 1,000 marbles. that look and feel exactly the same, but weigh just a tiny bit less. Several methods were proposed, all of them of insane complexity and industrial scale. One was gaseous diffusion, led by Urey. The idea was to convert uranium into a corrosive gas, uranium hexafluoride, and pass it through thousands of porous barriers. The lighter U-235 molecules would pass through the pores slightly faster than the heavier U-238. By repeating the process thousands upon thousands of times, the uranium could be gradually enriched. The problem was that the required plant would be the largest ever built under a single roof. Would need materials resistant to an incredibly corrosive gas that had not yet been invented, and would consume an astonishing amount of electricity. The other primary method was electromagnetic separation, championed by Ernest Lawrence. It used a large-scale version of his cyclotron, which he called a calitron. The idea was to ionize uranium atoms, accelerate them with powerful magnets, and make them trace a curve. The lighter U-235 ions would trace a slightly tighter curve than the heavier U-238, allowing them to be collected in separate containers. The problem was that the process was terribly inefficient. Each calitron could separate only milligrams of U-235 per day. To produce the kilograms needed for a bomb, they would need thousands of these devices, each with enormous magnets that would require so much copper that the Army had to borrow thousands of tons of silver from the U.S. Treasury to wind the coils. Faced with the uncertainty of which method would work, or if any would, Groves made a bold and enormously expensive decision. Do them all. He wouldn't bet on a single horse. He would build the entire stable. He ordered the acquisition of a vast tract of land in a rural, isolated area of Tennessee. There, in a valley surrounded by hills, a secret city would spring up from nothing. A city dedicated to the monumental task of separating atoms. They would call it Oak Ridge. And as the plans for this gargantuan industrial undertaking took shape, in a makeshift laboratory beneath the stands of a football field in Chicago, Enrico Fermi was preparing to take the next crucial step, to demonstrate that a self-sustaining chain reaction was indeed possible. The project was underway, and its scale already surpassed anything science had ever attempted before. While engineers planned the colossal factories of Oak Ridge, the central challenge remained the same: obtaining enough fissile material. The uranium-235 path was, as we saw, a problem of industrial brute force. It was a task of filtering and separation on a scale the world had never seen. The gaseous diffusion plant, named K-25, was being designed in Tennessee. When completed, it would be a U-shaped building nearly a kilometer long on each side, the largest building in the world at the time. Inside, thousands of miles of piping and pumps would operate in a near-perfect vacuum, circulating the corrosive uranium hexafluoride gas through countless porous nickel membranes. The technology for the membranes themselves didn't even exist at the project's outset. It had to be invented from scratch. The research and development effort to create a barrier with billions of holes per square inch, strong enough to withstand pressure and resistant to corrosion, was a Herculean project in itself. The plant would consume more electricity than a medium-sized city, and thousands of workers, most unaware of their work's ultimate purpose, would be hired to build and operate it. At the same time, in another valley of Oak Ridge, the electromagnetic separation plant called Y-12 was being built. This plant housed Ernest Lawrence's calutrons. Imagine rows upon rows of gigantic machines, nicknamed racetracks for their oval shape, each with a massive magnet at its center. As we mentioned, nearly 14,000 tons of silver from the U.S. Treasury were needed for the magnet windings, as copper was vital for the conventional war effort. Inside these machines, a beam of uranium ions would be shot through a magnetic field, separating the U-235 and U-238 isotopes into two distinct streams that were collected in small carbon receptacles. The process was incredibly inefficient. Most of the valuable uranium material ended up scattered across the internal walls of the vacuum chamber instead of in the receptacles. Young women from rural Tennessee who proved to be more dexterous and careful than the physicists were trained to operate the Calutron's complex control panels, adjusting voltages and currents without the slightest idea that they were separating the components of an apocalyptic weapon. At the end of the day, they meticulously scraped the machine's interiors to recover every microgram of the precious U-235. Initially, production was discouragingly low. Thousands of Calutrons, operating 24 hours a day, 7 days a week, were needed to produce significant quantities. Ultimately, the two uranium methods were used in tandem. The K-25 gaseous diffusion plant produced slightly enriched uranium, which was then used as feedstock for the Y-12 Calutrons, which enriched it to weapon grade, above 90% U-235. It was a cascading industrial process of astonishing complexity and cost, all to isolate a few kilograms of a specific isotope of a gray metal. Oak Ridge became a city of 75,000 inhabitants that appeared on no map, a community built around secrecy and a task that most of its residents did not comprehend. They saw trains laden with raw materials pass through and small, heavily guarded shipments depart, unaware that they were witnessing the production of the world's first nuclear fuel. But there was another path, an alternative route, that was perhaps even more scientifically audacious. Instead of separating the elusive U-235, why not create an entirely new element that was fissile? The theory was as follows. If you bombard uranium-238, the common and non-fissile isotope, with slow neutrons, the U-238 nucleus sometimes absorbs a neutron. This turns it into the unstable U-239, which quickly decays into Neptunium-239, and then, within days, into a completely new element with 94 protons, Plutonium-239. And theory predicted that Plutonium-239 would be even more fissile than Uranium-235. Furthermore, since plutonium was a chemically different element from uranium, it could be separated from unfissioned uranium through relatively simple chemical processes, thus avoiding the headaches of isotope separation. The idea was elegant and brilliant, but it posed a new and monumental challenge. To create plutonium, you needed an intense, controlled source of neutrons. You needed to build a nuclear reactor. This task fell to Arthur Compton's team at the University of Chicago, and the leader of the experimental team was none other than the Italian immigrant Enrico Fermi, arguably the last physicist who was a master of both theory and experimentation. Fermi was a practical and methodical genius. His plan was to build an atomic pile, literally a stack of ultra-pure graphite blocks interspersed with chunks of uranium oxide. The graphite would act as a moderator, slowing down the neutrons released by uranium fission, so they would be at just the right speed to be absorbed by other uranium nuclei and sustain the chain reaction. The purity of the graphite and uranium was absolutely critical. Any impurity could absorb the precious neutrons and stop the reaction. The chosen location for this historic experiment was not an isolated desert laboratory, but a makeshift space beneath the abandoned stands of Stagg Field, a football field in the heart of the University of Chicago campus. Day after day, during the autumn of 1942, Fermi's teams stacked 45,000 blocks of slippery black graphite and over 5 tons of uranium. It was a dirty, grueling job. The pile, a flattened sphere, almost 8 meters in diameter, was built layer by layer. It was crisscrossed by several cadmium control rods, a material that avidly absorbs neutrons. As long as these rods were inserted into the pile, the chain reaction could not begin. On December 2nd, 1942, everything was ready. A small group of scientists gathered on the chilly balcony overlooking the pile. Fermi, with his characteristic calm, directed the experiment. He ordered the control rods to be withdrawn inch by inch. The Geiger counters began to click, faster and faster. The tension in the room was palpable. Finally, at 3:25 p.m., Fermi made a quick calculation on his slide rule, smiled, and announced, "The reaction is self-sustaining." The pile, known as Chicago Pile 1, CP1, had gone critical. For the first time in history, humanity had initiated and controlled a nuclear chain reaction. The experiment ran for 28 minutes before Fermi ordered the control rods inserted to shut it down. Eugene Wigner, one of the Hungarian physicists, had brought a bottle of Chianti to celebrate. They drank in silence from paper cups. They had unleashed the power of the atomic nucleus. The Italian navigator, as they codenamed Fermi, had arrived in a new world. And now that they knew the process worked, it was time to scale it up in an unimaginable way. The success of Chicago Pile 1 was a monumental proof of concept. It demonstrated that a self-sustaining chain reaction was possible, and thus plutonium production was feasible. But Fermi's pile was a laboratory device. It produced a minuscule amount of energy, barely half a watt, enough to light a small bulb, and therefore negligible amounts of plutonium. To produce the kilograms of plutonium needed for a bomb, they needed reactors thousands of times more powerful. And a reactor of that power would generate such an immense amount of lethal heat and radiation that it couldn't be built beneath a football stadium's stands. They needed a remote, vast location with access to an almost limitless supply of cold water for cooling. General Groves, with his instinct for large-scale logistics, chose a perfect spot, an enormous expanse of semi-desert land in Washington state, along the banks of the mighty and cold Columbia River. This site would become known as Site W, or more commonly, Hanford. Here, on this desolate plain, the Manhattan Project embarked on building an industrial complex that would rival Oak Ridge in scale and complexity. Hanford's mission was unique: to construct the world's first large-scale production nuclear reactors, and, alongside them, gigantic chemical processing plants to extract plutonium from irradiated uranium fuel. The engineering firm DuPont, known for its expertise in complex and dangerous chemical plants, was hired to design and build the complex, a task they accepted reluctantly and for a symbolic profit of $1. At Hanford, 3 massive nuclear reactors were built: Reactor B, Reactor D, and Reactor F. Each was a graphite cube nearly 10 meters high, weighing 1,200 tons, and traversed by over 2,000 aluminum tubes. Inside these tubes, slugs of metallic uranium fuel were inserted. Water from the Columbia River was pumped through the tubes at an incredible rate to cool the uranium and prevent it from melting. The process was an industrial cycle of brutal elegance. Virgin uranium was inserted into the reactor. The reactor was brought online, initiating a controlled chain reaction. For months, the uranium was cooked in the intense neutron flux, transmuting a small fraction of its U-238 into plutonium. Then, the uranium slugs, now intensely radioactive, were pushed out of the reactor and dropped into a deep pool of water, the cooling pond, where they remained for several weeks for the most dangerous and short-lived isotopes to decay. The next step was chemical separation, and it was here that Hanford's scale became truly surreal. The cooled slugs were transported in heavily shielded rail cars to enormous processing plants known as canyons or Queen Marys. These were concrete buildings nearly 250 meters long, windowless, with walls over a meter thick. Inside, a fully automated, remotely operated chemical process dissolved the uranium slugs in nitric acid. Then, through a series of complex chemical steps involving bismuth and phosphate, a minuscule percentage of plutonium was separated from the unfissioned uranium and the highly radioactive fission products. The entire process had to be handled by remote control. Operators worked behind thick concrete walls and leaded glass windows, using periscopes and remotely operated cranes to move materials. No human could enter the processing cells once the process began. The radiation was so intense, it would be fatal in seconds. If something broke, it had to be repaired by remotely operated cranes and tools, or the cell had to be abandoned forever. These plants were, in essence, temples of remote chemistry, an engineering feat unprecedented. At the end of this long and dangerous process, what remained was a small amount of a plutonium nitrate solution, which was then converted into a small metallic plutonium button, about the size of a coin. Each button was the final result of thousands of tons of concrete, thousands of kilometers of piping, millions of liters of river water, and the labor of tens of thousands of people. Hanford, like Oak Ridge, became a secret city, with over 50,000 residents living in prefabricated camps and barracks, working on a project whose purpose was a mystery to almost all of them. They faced unexpected technical challenges. When the first reactor, Reactor B, came online in September 1944, it ran perfectly for a few hours, and then, mysteriously, shut down. The chain reaction stopped. Scientists, led by John Wheeler, were desperate. After a few hours of panic and feverish calculations, they realized that a fission product, xenon-135, an isotope not previously considered, was an extremely potent neutron poison, absorbing them and choking the reaction. Fortunately, DuPont engineers, purely as a precaution, had designed the reactor with more fuel tubes than the physicists had said were necessary. By loading these additional tubes, they were able to overcome the xenon poisoning and restart the reaction. It was a wake-up call that demonstrated how new and unpredictable this territory was. In early 1945, the first deliveries of plutonium, a silvery metal strangely warm to the touch due to its own radioactivity, began arriving from Hanford to an even more secret location, a place where all the project's threads would finally come together. While the gigantic factories of Oak Ridge and Hanford roared to life, the project needed a central nervous system, a brain, where all the theory, experimentation, and produced materials could converge for a single purpose: to design and build the bomb. In late 1942, Oppenheimer and Groves sought a location that met a very strict set of criteria. It had to be remote to ensure secrecy and security, yet accessible enough to receive supplies and personnel. It needed space for laboratories, workshops, and housing. Oppenheimer, who loved the landscape of the American Southwest, suggested an isolated mesa in northern New Mexico called Los Alamos. It was the site of a former boys' school, the Los Alamos Ranch School. It was perfect. Isolated, beautiful, and defensible. Groves agreed, and the Army quickly seized the land. Thus was born Project Y, the Los Alamos Laboratory, the secret city on the mountaintop. Within months, what had been a quiet school transformed into a bustling town of barracks, makeshift laboratories, and muddy streets, all surrounded by barbed wire fencing and patrolled by military police. Oppenheimer, the scientific director, faced the monumental task of recruiting the best scientists from across the country and the Allied world. He traveled nationwide, using his immense charisma and intellect to persuade Nobel laureates, promising young physicists, chemists, and engineers to leave their university careers and move their families to an unknown location in the middle of nowhere, unable to tell them exactly what they would be working on. He spoke to them of a task that could end the war, and they flocked. Hans Bethe, a master of theoretical physics, was appointed head of the theoretical division. Robert Bacher, an experimental physicist from Cornell, led the experimental division. Chemist Joseph Kennedy and metallurgist Cyril Smith handled the chemistry and metallurgy of uranium and plutonium. The great Enrico Fermi, after his success in Chicago, became a general consultant, a scientific pope, whose wisdom was sought on almost every problem. The atmosphere at Los Alamos was a surreal mix of academic rigor, military secrecy, and frontier life. The world's best minds lived in prefabricated housing, struggled with unreliable generators and water shortages, and raised their children in a community where the mailing address was simply P.O. Box 1663, Santa Fe, New Mexico. Scientists were organized into divisions, each working on a piece of the puzzle. The theoretical division, under Bethe's leadership, handled the fundamental calculations. What was the exact critical mass of U-235 and Pu-239? How much energy would be released? How would matter behave at the extreme temperatures and pressures inside a nuclear explosion? Conditions that had never existed on Earth before. The Chemistry and Metallurgy Division faced the challenge of purifying and shaping the nuclear metals. Uranium, and especially plutonium, proved to be incredibly difficult materials to work with. Plutonium, in particular, was a metallurgical nightmare. It had multiple crystalline phases, was highly toxic, and corroded easily. Turning the Hanford product into a precise, stable metallic sphere was a scientific feat in itself. Other divisions worked on detonation electronics, the hydrodynamics of explosions, and the development of instrumentation to measure the outcome. Life was compartmentalized. A physicist working on detonators was not allowed to know the details of plutonium metallurgy. Oppenheimer was one of the few people, along with Groves, who had a complete overview of the entire project. He moved between divisions, absorbing information, resolving disputes, and pushing his teams forward with tireless energy. He suffered immense strain, his weight plummeted, and his reliance on cigarettes and martinis became legendary. But he held the laboratory together through the sheer force of his intellect and personality. Los Alamos became a place of unparalleled intellectual intensity. Seminars and colloquia were constant. In the cafeteria, you might see Niels Bohr, who escaped occupied Denmark and arrived at Los Alamos under the pseudonym Nicholas Baker, discussing quantum mechanics with Richard Feynman, a brilliant young physicist who amused himself by cracking his colleagues' safes. It was a summer camp for geniuses, but with a grim, urgent purpose looming over everything. The final goal, the gadget, as they codenamed it, was always present, and as the project progressed, it became clear that they would need not one, but two fundamentally different bomb designs, each with its own set of diabolical challenges. In the Los Alamos laboratories, the objective was simple in its conception: quickly bring together a quantity of fissile material greater than the critical mass. If you managed to assemble a supercritical mass, the chain reaction would spontaneously initiate and propagate at an explosive rate, releasing an unimaginable amount of energy. The difficulty lay in the quickly. The mass had to be assembled in a millionth of a second. If it was too slow, the reaction would begin prematurely. The bomb would heat up, expand, and disassemble before a significant portion of the material had fissioned. It would be a fizzle, a radioactive firecracker, instead of a nuclear explosion. For uranium-235, the Los Alamos team devised a method that was, in principle, relatively straightforward. They called it the gun-type design. The idea was, literally, to build a gun. They would take two pieces of uranium-235, both below critical mass. One piece, the projectile, would be a hollow mass, like a cylinder with a hole in the center. The other piece, the target, would be a solid rod that would fit perfectly into the projectile. These two pieces would be placed at opposite ends of a gun barrel. To detonate the bomb, conventional explosives, such as cordite, would be used to fire the uranium projectile down the barrel at a speed of several hundred meters per second. The projectile would crash into the target, instantly forming a single supercritical mass. A neutron source, called an initiator, placed at the center, would provide the first neutrons to start the chain reaction at the precise moment. The concept was mechanically simple, similar to existing artillery. The physics was so well understood, and the method so straightforward, that Los Alamos scientists were extraordinarily confident it would work. They were so confident, in fact, that they decided it didn't need to be tested before use. The challenges were primarily ballistic engineering, building a gun that was light enough to be carried by an aircraft, but robust enough to function reliably. The resulting bomb, codenamed Little Boy, would be a long, slender device, essentially a modified naval artillery gun barrel enclosed in a bomb casing. The simplicity of the gun-type design relied on the properties of uranium-235. U-235 has a relatively low rate of spontaneous fission, meaning it rarely fissions on its own without being struck by a neutron. This allowed enough time for the gun mechanism to assemble the critical mass before a premature chain reaction could begin. However, as the first samples of plutonium began to arrive from Hanford in the spring of 1944, scientists at Los Alamos, led by physicist Emilio Segre, made an alarming discovery. The plutonium produced in a reactor was not pure. It contained a small but significant contamination of another isotope, plutonium-240. And Pu-240 had a spontaneous fission rate thousands of times higher than U-235. It constantly released a shower of neutrons. This discovery was a disaster for the gun-type design. If they tried to use the gun method with plutonium, the high spontaneous fission rate of Pu-240 would initiate the chain reaction the instant the two pieces of plutonium began to approach each other. The bomb would pre-detonate, producing a fizzle with miserable efficiency. The gun's speed was simply too slow to win the race against the Pu-240 neutrons. For a moment, It seemed that the entire Hanford effort, the secret city, the giant reactors, the chemical processing canyons, had been in vain. The plutonium, which they had created with such effort, seemed useless for a bomb. The project faced its greatest scientific crisis. It was at this point that a radical idea, which had been considered and dismissed as too difficult, became the only hope for plutonium. The idea was implosion. Instead of firing one piece of fissile material into another, what if you could take a subcritical sphere of plutonium and compress it uniformly from all directions at the same time? By compressing it, you would increase its density. And by increasing its density, you would bring the plutonium nuclei closer together, reducing the distance neutrons had to travel to find another nucleus. This would drastically reduce the critical mass. A subcritical sphere could, in a fraction of a microsecond, become supercritical. The implosion assembly speed would be thousands of times faster than the gun method, fast enough to win the race against plutonium's pre-detonation. The idea was championed by physicists like Seth Nettermeyer, but implementation was an engineering nightmare. To compress a plutonium sphere perfectly, they needed to surround it with conventional explosives and detonate them all simultaneously, creating a spherical, converging shockwave directed towards the center. If the shockwave was not perfectly symmetrical, it would simply crush the plutonium sphere irregularly and spit it out, failing to achieve the necessary compression. The problem was how to transform the diverging shockwaves from multiple detonation points into a single, spherical, converging shockwave. The solution was one of Los Alamos' greatest breakthroughs, the explosive lens. They developed an incredibly complex system that used a combination of fast and slow explosives molded into precise shapes like optical lenses. When detonated, these lenses shaped and focused the expanding wave, turning it into a perfect spherical shockwave that rushed inward. The design of these lenses required the help of mathematician John von Neumann, who performed massive hydrodynamic calculations using IBM punch cards to determine the exact shapes. The work of manufacturing and testing these high-precision explosives fell to the Explosives Division, led by Harvard chemist George Kistiakowsky. They spent months conducting tests at remote canyons, detonating charges, and using high-speed cameras and X-rays to study the symmetry of the implosions. It was dangerous and frustrating work. But slowly, methodically, they solved the problem. The resulting device, codenamed Fat Man, would be a complex sphere of explosives, tamper, neutron reflectors, and at its heart, a small, orange-sized sphere of plutonium. It was a much more elegant and efficient solution than the gun method, but also infinitely more complex and uncertain. Unlike Little Boy, there was no way to be sure Fat Man would work without a full-scale test. During the early years of the Manhattan Project, a constant shadow loomed over the scientists, the fear of the Nazi bomb. Fission had been discovered in Berlin. Germany had world-class scientists, including the brilliant Werner Heisenberg, one of the fathers of quantum mechanics. The assumption driving the entire project was that they were in a desperate race against the Germans. Every delay, every technical challenge was measured against the imagined progress of Hitler's nuclear weapons program. This psychological pressure was immense and defined the urgency felt by Oppenheimer, Groves, and everyone at Los Alamos. They imagined Heisenberg and his team working feverishly in an underground laboratory somewhere in the Black Forest, perhaps months or even weeks ahead of them. This belief, though based on very little solid intelligence, was a powerful motivator. It fueled the long nights of work, justified the enormous expenses, and silenced many of the moral doubts some scientists were beginning to feel. To find out what the Germans were actually doing, the Manhattan Project created its own intelligence branch, a scientific mission codenamed ALSOS, the Greek word for grove, a play on General Grove's last name. The ALSOS mission was comprised of a team of soldiers, intelligence agents, and scientists, with physicist Samuel Goudsmit at its head. Their job was to follow closely behind Allied troops as they advanced through Europe after D-Day, with the mission to capture German scientists, confiscate documents, and seize any nuclear materials they could find. As the mission progressed through France, Belgium, and finally Germany in 1944 and early 1945, they began to piece together a picture of the German nuclear enterprise. And the picture that emerged was astonishing. They discovered that the German program, the Uranverein, Uranium Club, was small, disorganized, and suffered from intense rivalry among its key scientists. They were light years behind the Manhattan Project. Heisenberg, though a brilliant theoretician, appears to have made several fundamental errors. In a crucial calculation, he grossly overestimated the critical mass needed for a uranium bomb, concluding it would require tons of U-235, which made it seem impracticable. This contrasted directly with Frisch and Peierl's calculation in Britain, which had estimated the critical mass in kilograms. Furthermore, the Germans failed to produce graphite of the purity needed to use it as a moderator in a reactor, forcing them to rely on heavy water, an extremely scarce resource that Norwegian commandos and Allied bombing raids took pains to destroy in a series of audacious strikes on the Vemork plant in Norway. The Germans never managed to build a self-sustaining nuclear reactor. When the ALSOS team found Heisenberg's laboratory in a cave in Haigerloch in southwestern Germany, what they found was not a nearly finished weapon, but a subcritical experimental reactor, a pile of uranium cubes hanging from wires and submerged in a tank of heavy water. They were roughly at the same point Enrico Fermi had been in Chicago more than 2 years earlier. For Goudsmit and the ALSOS team, the discovery was a stunning revelation. The feared Nazi bomb was a ghost. There had never been a real race. The Manhattan Project had been racing against a shadow. The news reached Los Alamos, and the reaction was mixed. On one hand, there was immense relief. The threat that had tormented them for years was not real. But for some, especially scientists like Leo Szilard and Joseph Rotblat, the discovery fundamentally changed the project's moral justification. They had begun their work out of fear that Hitler would get the bomb first. With Germany defeated and the Nazi threat eliminated, what now was the purpose of continuing? Rotblat, a Polish physicist, was the only scientist to leave Los Alamos on grounds of conscience once it became known that Germany did not have the bomb. For most others, however, the project's momentum was already too great to stop. The war in the Pacific against Japan remained brutal and bloody. The bomb had become a tool to end that war and save American lives. Moreover, the gadget had become a fascinating scientific and technical challenge in its own right. They wanted to see if their creation would work. The German ghost had vanished, but the monster they had created in the New Mexico desert was about to be born, and its momentum was now unstoppable. The original justification had faded, but the bomb now had a life of its own, and it demanded to be tested. The story's focus shifted from a race against an imaginary enemy to a confrontation with their own creation. As the implosion design of Fat Man took shape, an undeniable truth became clear to Oppenheimer and his team. Unlike Little Boy's gun-type design, the The plutonium device was too complex and too uncertain to be used without a full-scale test. There were too many variables. The perfect synchronization of the 32 detonators, the formation of the symmetrical shockwave by the explosive lenses, the complex metallurgy of plutonium compressing under extreme pressures. A failure in any of these components, and the device would be a dud. They needed to test it. They needed to detonate an atomic bomb on their own soil before considering using one against the enemy. The decision to conduct the test, codenamed Trinity, marked the beginning of the project's final and most tense phase. The first task was to find a suitable location. It had to be extremely remote to maintain secrecy and contain the blast, yet close enough to Los Alamos for logistics. After exploring several sites, they chose a desolate, uninhabited corner of the New Mexico desert within the Alamogordo bombing range, a place the early Spanish explorers had called the Jornada del Muerto. It was a flat, austere, and almost lifeless landscape, perfect for their purpose. At the center of this site, engineers built a 30-meter-high steel tower. On top of this tower, the gadget would be assembled and detonated. Around Ground Zero, concrete observation bunkers were established at safe distances, and a massive network of instrumentation was deployed. Seismographs, high-speed cameras, radiation detectors, and pressure sensors, all connected by kilometers of wiring to record every millisecond of the world's first nuclear explosion. The final assembly of the gadget was a tense and meticulous process. The plutonium core, carefully machined and nickel-plated, arrived from Los Alamos in an Army sedan, transported in a special, shock-absorbing case. At an abandoned farmhouse near the test site, the assembly team, led by physicist Norris Bradbury, began the delicate work. First, they assembled the explosive lenses, fitting the pieces of fast and slow explosive together like a giant three-dimensional puzzle around a uranium tamper. Then, at the very last moment, the device's heart, the plutonium core and the polonium-beryllium initiator, was carefully inserted into the center. The final assembly took place atop the unstable steel tower in the middle of the desert. The team worked in a small corrugated metal shack on the tower's platform, battling wind and dust. At one point, the core got stuck as they were inserting it. For an instant of panic, they thought they would have to dismantle everything. But with a bit of gentle persuasion, it finally slid into place. The gadget, a sphere almost 1.5 meters in diameter covered in wires, was armed and ready. The test date was set for the early morning of July 16, 1945. As the hour approached, the tension at Los Alamos and the Trinity site became almost unbearable. Scientists, technicians, and military dignitaries began arriving at the observation bunkers. Groves was present, as were Oppenheimer, Fermi, Bethe, Kistiakowsky, and many others who had dedicated the last 3 years of their lives to this moment. Oppenheimer, gaunt and exhausted, seemed a shadow of his former self. The weight of responsibility was immense. There was a small but persistent theoretical concern, raised by Edward Teller, that the explosion might be so hot that it would ignite the Earth's atmosphere, burning up the entire planet. Hans Bethe had performed the calculations and shown it to be impossible, but the fear lingered like a whisper in the back of their minds. To heighten the tension, the weather turned against them. The night before the test, a violent thunderstorm erupted over the desert, with lightning and torrential rain. A detonation under those conditions would be a disaster, scattering radioactive fallout unpredictably and blinding the instrumentation. The test, scheduled for 4 a.m., had to be postponed. The meteorologists were under incredible pressure. Oppenheimer and Groves discussed options. Canceling would mean a delay of days and a terrible psychological blow. Finally, the meteorologists predicted a window of calm around 5:30 a.m. The decision was made. The test would go ahead. In the bunkers, the scientists waited. Some placed bets on the bomb's yield, from a complete dud to an explosion that would exceed all expectations. Fermi, in a gesture of dark humor, offered to bet on whether the bomb would ignite the atmosphere or not. Others, like Kistiakowsky, bet a month's salary that the device would work. The final countdown began, broadcast by radio to the bunkers. -20 minutes, -10 minutes, -5 minutes. In the darkness before dawn, amidst the silent desert of the Jornada del Muerte, the world held its breath, awaiting a sunrise that would not come from the east. In the south control bunker, about 10 kilometers from ground zero, the announcer's voice echoed over the loudspeakers. Marking the final seconds, the atmosphere was a mix of scientific expectation and primordial terror. Observers had been told to lie on the ground, feet pointing towards the blast, and not to look directly until the shockwave had passed. At 5:29:45 a.m. local time, the countdown reached zero. For a fraction of a second, nothing happened, and then the world changed forever. There was no sound at first, only light. A light of an intensity no human had ever witnessed. A brilliant flash, not like the sun, but like a magnified sun, illuminating the desert and surrounding mountains with a spectral clarity, brighter than midday. Physicist Isidore Rabi later described how the light filled the sky, a sunrise such as the world had never seen, a green light, superterrestrial, supernatural. Those who risked a glance saw a rapidly expanding hemisphere of light, changing color from violet to green, and then to blinding white. The 30-meter steel tower itself was instantly vaporized. Immediately after the flash, a searing, furious fireball began to rise from the ground. It was a terrifying yet hypnotic sight, a sphere of plasma at millions of degrees, writhing and ascending, consuming the desert air. Then, almost a minute later, the sound arrived. First, a sharp, deafening crack, the direct shockwave traveling at the speed of sound. It was followed by a continuous, thunderous rumble, a roar that seemed to come from all directions at once, reverberating through the mountains and shaking the ground beneath their feet. It was the sound of the atmosphere itself being torn apart. The fireball, as it rose, began to cool and suck up dust and debris from the desert floor, forming the stem of what would become the iconic image of the nuclear age, the mushroom cloud. The cloud quickly ascended, reaching 12 kilometers in height, an ominous column looming over the landscape. In the bunkers, the reaction was a mixture of euphoria, awe, and a profound sense of dread. Kistiakowsky, who had bet the device would work, ran to Oppenheimer, clapped him on the back, and reminded him he owed him $10. Kenneth Bainbridge, the Trinity test director, turned to Oppenheimer and spoke words that would become famous. "Now we are all sons of bitches." Oppenheimer's reaction was more silent and profound. He would later recall that upon seeing the fireball, 2 lines from the sacred Hindu text, the Bhagavad Gita, came to his mind. One was, "If the radiance of 1,000 suns were to burst at once into the sky, that would be like the splendor of the Mighty One." The other, more somber, was, "Now I am become death, the destroyer of worlds." Trinity's success was absolute. The explosion was equivalent to about 21,000 tons of TNT, a figure that exceeded most expectations. The implosion design, the project's riskiest gamble, had worked perfectly. The gadget was not just a laboratory device, it was a viable weapon. The desert at Ground Zero had been transformed. The sand had melted from the intense heat into a pale, green, radioactive glass, later called trinitite. Science had fulfilled its promise. The years of theory, experimentation, engineering, and construction had culminated in that blinding flash. The scientists' work, in essence, was done. They had conceived and given birth to a completely new power in the universe. Now, the question of what to do with that power passed from their hands to those of politicians and the military. Thousands of kilometers away, in Potsdam, Germany, President Harry Truman received a coded message. The baby has been satisfactorily born. The world had entered, whether it knew it or not, the atomic age. With the success of the Trinity test, the Manhattan Project transitioned from a scientific endeavor to a military operation. The gadget had proven the implosion design viable, and the gun-type design, Little Boy, was considered so certain to work that it didn't require a test. Now, the task was to produce the weapon components, transport them across the Pacific, and assemble them for combat use. The pace accelerated frantically. While the Trinity scientists were still analyzing the explosion data, Little Boy's components were already en route. The uranium-235 projectile and other non-nuclear parts were loaded aboard the heavy cruiser USS Indianapolis in San Francisco. The ship set sail on July 16th, the same day as the Trinity test, on a high-speed mission to Tinian Island in the Marianas, which had been designated as the operations base for the attack. Tragically, after delivering its precious cargo, the Indianapolis was sunk by a Japanese submarine in what became one of the worst naval disasters in U.S. history. Meanwhile, the uranium rings forming Little Boy's target and the components for Fat Man, including its plutonium core, were flown to Tinian. On the island, a special detachment, the 509th Composite Group, had been established under the command of Colonel Paul Tibbets. It was a unit of B-29 bombers specially modified to carry the enormous heavy bombs. On Tinian, air-conditioned buildings with strict security measures were constructed for the final assembly of the weapons. A team of scientists and technicians from Los Alamos, dubbed Project Alberta, was sent to oversee this last crucial step. The decision-making process on how and where to use the bombs was already underway. A target committee comprised of military personnel and scientists, including Oppenheimer, had been deliberating for months. Several Japanese cities were considered. Criteria included that the target should have military significance, that it should not have been significantly damaged by conventional bombing so that the atomic bomb's effects could be clearly evaluated, and that the city's size should be large enough to demonstrate the weapon's power. Kyoto, the ancient imperial capital and a cultural center of immense value, was on the initial list, but was removed by Secretary of War Henry Stimson, who felt its destruction would cause lasting resentment and hinder post-war reconciliation. Finally, a list of primary and secondary targets was selected. For the first mission, the primary target was Hiroshima, an important military base and industrial center that had previously been very lightly bombed. On Tinian, the assembly team worked feverishly. Little Boy was assembled in a bomb loading pit, a relatively straightforward process involving placing the gun barrel, explosives, and uranium components inside its casing. On August 6, 1945, Tibbets' B-29, which he had named Enola Gay after his mother, took off from Tinian with Little Boy in its bomb bay. The bomb was armed in flight. At 8:15 a.m. Hiroshima time, the bomb was dropped. It detonated about 600 meters above the city, creating a fireball and shockwave that annihilated the city center and killed tens of thousands of people in an instant. The scientific journey that had begun with a perplexing letter about barium in Berlin had reached its terrible conclusion. 3 days later, with Japan still refusing to surrender, the second mission was prepared. The primary target was the city of Kokura, but it was covered by clouds. The B-29, named Boxcar, diverted to its secondary target, Nagasaki. Fat Man, the complex plutonium implosion device, was dropped on the city, detonating with a force equivalent to that of Trinity. The bomb devastated the Urakami Valley, although the city's mountainous terrain limited some of the destruction. 6 days later, Japan surrendered. World War II had ended. For the scientists of the Manhattan Project, the end of the war brought a mixture of relief, pride in their technical achievement, and a deep and often tormented sense of responsibility. They had begun their work out of fear of a Nazi weapon, but they had ended up creating a world-altering power and delivered it to humanity. Many of them, like Oppenheimer, would spend the rest of their lives advocating for international control of atomic energy and warning about the dangers of a nuclear arms race. Others returned to academic life, trying to put their work on the project behind them. But none could escape the fact that they had been the architects of a new era. Fundamental science, driven by curiosity about the nature of the atom, had merged with engineering on a massive scale and military necessity to produce the most terrible weapon in history. The journey from the fission of the nucleus to the fission of cities had been completed. And with that flash, the scientists' work was done. World of theoretical physics, of blackboards and feverish dreams, had given birth to something tangible, terrible, and definitive. Now, simply rest.